Just send me.
All right, let's get started. So on Thursday, we won't have class in the room, so normally what I do is I give a NetLogo tutorial today to prepare you for Lab 4, which is formally assigned this week, although some people have already turned it in. And then on Thursday, we would do this lecture. So, because I can't be here on Thursday, I'm swapping it around, so we're going to jump straight into Unit D. And if you need the extra help with the NetLogo, then that tutorial is online as Lecture C2, but it's in a couple other places too. Basically, if you go to Lab 4 and you want the extra help for the tutorial, a lot of you will be able to complete Lab 4 without it, but if you want it, it's already linked onto those Lab 4 slides, or Lab 4 links. And so that is already an option available. Otherwise, Lab 5 next week will be our first arena lab. So we eased into simulation with Excel and then NetLogo for some kind of simple examples, and then we'll start you'll start with the manufacturing system and a queuing system in Lab 5. That lab is also totally available, so if you wanted to work ahead and work on it, that's fine too. But otherwise, if you'd like to come in and get the help from the TA, then you're welcome to do that. I'm a little disappointed that Lab 1 isn't graded yet, so I'm kind of pushing on the TAs to get all of those graded. I think there's at least one section is totally all graded, and then the others are a little slower than I like, and so we're working on that. So homework, but the solutions for the homework should be online, and again, there are these Canvas activities. Again, you only have to do like 5 of them in the semester. All the rest, your low scores are dropped, but they've been rolling along. And so if you're looking for extra practice that's sort of outside of the homeworks, then recommend checking out the Canvas activities that come from the lectures in the book. Otherwise, homework C2 is available, so there's going to be 2 homeworks before the midterm, C2 and D2. C2 are these 2 questions that are generating some random numbers in one and testing for randomness in the other. A bunch of people have already submitted this one. I think it's relatively straightforward. Homework D2, which is also available, is going to be a little more complicated for some. It requires you to remember some of your calculus, but I've adjusted kind of the due dates so that there's going to be plenty of time for us to cover this content in class, and you'll be able to turn this in and still get the solutions back for D2 before the midterm. So the content on this homework will be covered on the midterm, and you should view this as practice for the midterm. This homework is sort of the hardest thing we've had to do. I'd say the hand simulation would be the most tedious thing we have to do, but traditionally this homework, D2 that's coming up, was the sort of most difficult content so far. So make sure to take a look at that ahead of time. It's just 2 questions. You're generating random variates. This is kind of the topic of lectures E1 and E2. And if you have questions, it's great to get those earlier than later. But again, we should have plenty of time in class to work examples and take questions and so on. I do have a lot of extra help online for these homeworks, I think both C and D. So take a look at those as well if you need that help elsewhere. The homework C2, I put this on the homework, but some people, if you've never seen this notation before, A mod B means the remainder when you divide A by B. So, if you did 15 mod 2, then because this is an odd number, then that remainder is equal to 1. In the context of the homework, almost always you're dividing by a power of 10. So if you did like 1752 mod 100, then you end up getting 52 out. So effectively by dividing by this power of 10, you're sort of just extracting these lower 2 digits. So that's pretty much all you need to do for that homework with respect to this modulo operator. Make sure to show your work on the homework. So in question 1, include your formulas. So question 1 is very much plug and chug, but we want to make sure that you're plugging into the right formula. So make sure that you make that clear. And in question 2, it's going to be easy to use a table, which is kind of like how the book solves the problem. In that case, you can put your formulas kind of in the rows of the table, like over on the side. And then that way you can just have, say, this is the formula I'm using, and then just populate the table with the numbers. So I don't need to see you plug in that over and over and over again. Because a lot of them are just subtraction or something like that. So kind of, follow the book's examples, and if you do it like the book does, then that'll be what we expect in the solution. All right, any questions about homework C2? Like I said, homework D2, which I don't think a lot of people have looked at yet, but I'm going to apply. So normally the way these things are due is they're due on a particular day, but I let you turn them in like 5 days after that. But it's a 20% deduction per day. So what I'm going to do for this one is I basically make it due on a particular day, but if you look at the homework, inside the homework, it says the kind of extended due date is the sort of the last day you would normally be able to submit it. So basically it's saying there's no late policy for homework D2. The flip side of that is if you view the last day you can submit it as the due date, there will be like no way to turn it in late. So most other homeworks you can turn in late, you get like a little deduction, but in this case, it's either in or it's not. But that will allow the solutions to get released with several days before the midterm. So that was kind of the trade-off there. There's going to be this Canvas activity that's not available in Canvas activity F, which basically once E1 is done, then F will become available, and it randomly samples from all the Canvas activities before it. And it's meant to be a midterm review. You can take it as many times as you want, and it's actually worth like 3.5 times the points of a normal ICA. And so if you complete it and you score well on it, and most of these things, like 99% of the questions are ones you've seen before, then considering the way Canvas drops things, it drops like whatever the worst 7 assignments, and so this can end up kind of, compensating for a lot of other assignments and things like that, and it's meant to sort of force you to revisit questions that you may have not seen for several weeks. And so that's how that ICA is. And that's also why it's not due yet, because I have to wait for all the other Canvas activities to be due, because it's just going to have all of their questions on it, and you'll be able to take it as many times as you want before the midterm review. And then Lecture F will be the midterm review. And so that will be, I think October 8th is a Tuesday, so Lecture F, the midterm review, will be the Thursday before that. So whatever that is, October 3rd or something like that. I'm basically just going to have a kind of a greatest hits of the slides that have come before, the things that I think are important. But it's primarily designed for you guys, so if you want, we can go through those slides then, or if you just have questions, we can answer those questions, we can work problems, whatever would work best for you. And so then you'll have the weekend to study and also get access to the homework solutions for homework D2, and then you'll come back in and we'll have the midterm in on that Tuesday, and we'll start back up with class after that. So that's the schedule going forward. Any questions about that? All right, so just another reminder, we've already had, I think, at least one team that is thinking about submitting to this, and I've given them approval to form. So there's, as an alternative to your final project, which will be sampling from systems that you naturally see around campus or around Tempe, around Phoenix. The alternative is you can enter this Rockwell Arena competition where they provide you data and a project, and then you work on it in competition with other teams at similar stages in their career from across the nation, and then the finalists get picked to go to this. Question.
Is there a way that we can get the fee for the application submission waived?
I can ask. In the past, I've gotten the school to cover it. We had a different director then, so I can ask that. And some student groups have also covered it in the past. So if I have to get on a plane right after this class, but if you send me an email so that I remember, then I will send up the ladder at the school. And I think we should have discretionary funds for this, but I don't want to promise anything because it's not my purse strings. Yeah.
For the note sheets that we are allowed to bring with us for the exam, is it only like just formulas, or can we write anything we want in them?
You can write anything you want on these sort of crib sheets here, just as long as it's not photocopied out of a book. Like I say that I want them handwritten. I've actually made exceptions in the past where it could be typed, but it's got to be that, like, when you turn in your exam and we look at it, it's got to be clear that you constructed it as opposed to you just copied out of a book or copied out of a solution set or something like that. I just want to force you to actually see the stuff and copy it because I think that helps with studying. And then, but what you put on there, it is totally up to you. If you would like to just copy a solution set down, that's fine, just as long as you're copying it and not a photocopier's copying it. All right, and then other competitions as well. All right, any other questions, admin stuff? I hope you, yeah.
Those lab teams, when do we have to have those by?
Oh, so yeah, I'm just telling you this stuff because these things are due at the end of the semester, but after the midterm, then we'll start getting into all of that. So basically, I have a little assignment that'll come in, I don't know, like a week and a half after the midterm, and it will ask you to form your teams. And so then after that, there'll be an assignment like a week after that, or a week and a half after that, where you'll sort of propose the project you're gonna do. So the timeline, I've got that all managed. And so if you're not interested in these competitions, forget about the final project and forming the teams until after the midterm. All right. Anything else? Okay, so let's do an attendance question. Up front, it's a little bit of a different thing here. And the question is there class on Thursday? Let's just put that in question 1. And if you don't know, talk to your neighbor. So again, that was, is there class this upcoming Thursday? Is there class in this room this upcoming Thursday? Oh, and also, so I do have had office hours posted. My office hours happen to be on Thursday, and so I don't arrive back until after them, so I have to cancel office hours this Thursday as well. But if there's particular questions that you have about the homeworks or whatever, I may have some time on Friday I could book, and so we can set up an appointment. Yeah. So just for the first, so I may ask more, but for the first question, it's just, is there class on Thursday? Because I covered that earlier. So write a yes or no answer. Under question 1, just write yes or no. That's your attendance question. All right, so let's move on. So now we have to get into probability. I have to motivate why. We have to review probability, and so hopefully this is starting to become kind of clear. We said that these DES simulation models characterize realistic variation. So I've given this timeline example where people arrive to an airport, and we might, coarsely say they arrive 1 every 20 minutes or 1 party every 20 minutes, but we don't actually know, sometimes they arrive sooner and sometimes they arrive later, sometimes they arrive in groups of 4, sometimes they arrive alone. So there's a lot of variation in reality, and that variation can be very challenging. And so as opposed to modeling the variation directly, we can indirectly model it with this stochastic approach, where we just assume that actually this variation is sourced randomly, even if it's not actually sourced randomly. So our goal then is to build a random process that well fits the distribution of data that we see in reality. That's the stochastic approach. So that's why I define stochastic. I claim that's the right definition of stochastic. But another view of stochasticity, which is a totally fine view, is that uncertainty and complexity are sources of randomness. So the way you'll learn about stochasticity in some of your other classes is that ideally we'd like to build simple models without any randomness, but whenever we run those, then they vary from reality. So it's almost like our uncertainty in our model is a source of noise. And in order for us to then augment our simplistic models to better fit reality, we have to model that noise. So that's kind of the 2 perspectives on stochasticity. You're either making a conjecture that the world is random even when it's not, just because it's easier for modeling, or you're taking a simplistic view of reality that is, because of your uncertainty, is going to be plagued by noise, and you need to model that noise, and so that's what you're doing. Either way, we seem to care about, randomness, and so we need to have a way to deal with randomness. And the way we deal with randomness is through probability theory. Now, probability theory is a branch of a much more sophisticated mathematics called measure theory. And measure theory is basically defined to give us tools to handle things that look like mass. Now, just sort of brainstorming, what do you think is similar about probability and mass? And by mass, I mean like this marker has mass. This marker cap has mass. This marker without its cap has mass. Together, the marker and cap together have mass. What's similar about this marker and about, say, probability? Any thoughts? Take 30 seconds. Talk to your neighbor. What's similar about mass and probability? Why would a theory defined to understand things that have mass be then so easy to use to understand probability? What do you know about probability that seems like mass? So go ahead and chat about it for about 30 seconds and we'll come back. All right, let's bring it back together. So what do you guys think? What is the analogy? How is probability, how is it analogous to mass? What is the mass and probability and vice versa? How do those two things relate? What properties does mass have that probability also has? Any thoughts? If there is a 30% chance that it's going to rain, and there is a 20% chance that it is going to snow, and those things are mutually exclusive, what is the chance that it is going to rain or snow? 30% chance rain, 20% chance snow. Anybody? 50%, right? So 20% chance rain, 30% chance snow. So 20% rain, 30% snow. So any precipitation whatsoever is 50%. 1 gram cap, 3 gram marker, 4 gram cap and marker. That's the relationship here. That's what we were trying to capture here, is that in probability, we've got these events like rain and snow, and we're going to associate with them things that are analogous to mass. And so long as those events don't overlap, if you're wondering how much the events together weigh, you add their weights together. And so that's kind of the why you hear things like density and mass are mentioned over and over and over again when we talk about probability, because they all come from this theory, which is sort of graphically depicted here. There are these things called measures, and mathematically they have certain properties that we count on. If you take a measure that's mu of an object, and you cut the object into 3 parts, then the measure of the subparts add up to the measure of the whole part. Not every mathematical function is like that, but if it is defined as a measure in a measure theory, it has to be defined that way. Similarly, if I've got a long continuous object, and I cut it up into an infinite number of parts, and those parts might get very, very tiny. If I add them all up together, the mass that I add up from each subpart should add up to the total part. And so that's something we count on. When we talk about mass and conservation of mass, we don't think if we cut a table in half and weigh the two halves, that suddenly we'll get any more than the whole table together. And it's similar with probability. And so this framework about measures was built to talk about things that are mass-like, and then it got specialized to talk about probability. And so that's where this language is coming from. And what I'm hoping to get to by the end of this lecture is to get you to a point where if you look at a probability density function, you'll forget about the probability and think about it like a mechanical engineer would, thinking about the density of this table. So we'll get there. So let's define a couple of things. Random variable. So random variable is neither random nor a variable. It's an unfortunate term. A random variable is a function that maps a set of outcomes in the real world to the real number line, something that we can then do math on. So we have outcomes, which are mutually exclusive results of an experiment, and each outcome needs to then get mapped to something. So as an example, if I've got 5 coins, and I throw them all up into the air, and they come down, the outcome is that I've had 5 coins and they landed in particular configurations. But I numerically represent that as the number of heads that landed. So when I look down at the coins, I count the number of heads. So I've mapped an outcome in the real world to a particular number. And then that number, now I can do math on that number. So random variable maps outcomes to points in the reals. We call those outcomes the so-called sample space. We'll use this omega for that. And all of those outcomes are mutually exclusive, so they can't both occur at the same time. And we refer to the range of the random variable as the set of numbers in the real line that correspond to all of the outcomes. So if I take every possible thing that can happen, and I see every possible number that can be mapped to that thing, those set of numbers is the range of the random variable. So that's sort of formally how we define a random number, a random variable. And so in your upper division classes, whenever you see a random variable, you see it written like this, as a function. Sometimes we actually use different things other than the real number line here. Sometimes we get more specific in the outcome space. For simplicity, we often drop this and just call it x. And most likely, up to this point, that's the way you viewed it, as just x. But as you start getting into more sophisticated stochastic operations research, then you're going to start seeing things like this in the literature about different methods and statistical methods and so on, and that's where that comes from. It's a mapping from the real world into the numerical world. No randomness whatsoever yet so far. But it lets us deal with randomness. But we first need this concept of an event. And this is unfortunate that in this class we've already defined event in a different context. But this event isn't just in the probabilistic context. An event is a set of outcomes. Outcomes are mutually exclusive. They come from the sample space. Events are sets of them. So an event can have one outcome in it, in which case they're sort of the same. So these outcomes up here, a 6-sided die shows 4 dots. Or Jeremy is the only student in class. Those are 2 outcomes because they're kind of mutually exclusive from every other outcome. They are also events that way because an event can have just one outcome in it. But events also can generalize to other cases. So I can say the 6-sided die shows at least 4 dots. Well, that's 4, 5, and 6. Those are 3 outcomes bundled into one. And I can say Jeremy and maybe others show up in class. So this one is Jeremy's in class. This one is Jeremy is the only one in class. There's a lot of different ways that Jeremy could be in class, but only one way that Jeremy could be the only person in the class. And so once you have multiple outcomes grouped together, we call that an event. And that term event is useful because that's where we actually assign probability. That's what actually gets the weight. That's what actually gets the mass. And so the probability measure, which we'll often write PR, or sometimes you just write P, this is a measure, so it uses that term from measure theory, that can assign a number to each of your events. And so that number is what we're going to call the probability. You can think of it as a weight of the events. And that's useful because it means that if you take an outcome out of an event to create a new event, it's necessarily going to weigh less because you've like taken the cap off the marker. If you take another one out, it's going to weigh less. The probability is going to go down. If you add outcomes in, it's going to weigh more. And so that's where we get kind of this weight interpretation, and that's why the event weights are the sum of the outcome weights inside them. Now the weight of the whole sample space is 1. So that's the weird thing about probability. This table weighs less than this table. Now, but we're saying, but in the world that we care about, we kind of normalize by the weight of one of these tables and just call them a unit weight. So in probability, our unit weight is the outcome space. We say these are the only outcomes we care about. That's like saying the only mass that we're going to deal with is this table's mass, and so we're just going to divide everything by the mass of the table so that all the masses add up to 1. And so the weight of the sample space here is the is 1. So from there we can now we went from outcomes to numbers, and then we defined events as a set of outcomes. We assigned probability to those events. And so now we've almost got everything that we sort of need here. So we can now define discrete random variables. And these are variables whose range comes from a finite or a countable set. So we're saying that outcomes in the real world, when you map them to the real number line, then that mapping is only going to map to basically things that we can count. It's not going to map to an interval. It's going to map to a number. So those coins, that's a discrete random variable because I can count how many heads come up. It's either 1 head, 0 heads, or maybe all the way up to 6 heads, because if I threw up 6 coins. But I can count all of those possible numbers that I've mapped those outcomes to. Now for each one of those, I can then have a shorthand where I say the probability of the number on the real line. And what I actually mean is the probability of the event induced by the mapping of the random variable that links that real number to an outcome. And so that's like the long way of saying it, and that's kind of, if you wanted to do something mathematically rigorous, that's the way you'd have to say it. But we just use these shorthands where we just say the probability of the number on the real line. But that's what that means, is it's linking to some outcomes in the real world somewhere. The probabilities all have to be positive, and they all have to add up to 1, because again, the mass of the sample space adds up to 1, and these are all of the outcomes from the sample space, so when you add them all up together, they have to add up to 1 to give you the mass of the whole sample space. So these are just definitions we're getting through here. Example, the number of jobs arriving in 1 week at a job shop, that could potentially be infinite. It doesn't mean that, there could actually be limitations, but without any other information, this could be a giant job shop, and so we have no reason to bound it. But we still call it a discrete random variable because we can count all of those possible outcomes. And so those outcomes are easy to map to the real line. They're just the number of jobs arriving. So, no jobs arrived this week or 1,000 jobs arrived this week, but I can count them. That's what makes it a discrete random variable. So any questions on this discrete stuff so far? It should just be a review of stuff you've seen in 380, maybe 385, if you're taking 385 concurrently. All right, so a little more, a more concrete example here. This random variable maps the number of spots face up on a die to these 6 numbers. So it could map from 0 to 5, but this random one mapped from 1 to 6. And so we assume that the die in the real world is weighted so that the probability of a given face is proportional to the number of dots on the die. And so that's what gives us the numerators here. We're saying that it is 6 times more likely for 6 dots to show than 1 dot to show. So, but why is the denominator 21 in all of these? Yeah. We didn't, well, that in this case, I actually haven't done the experiment. I'm just describing what would happen if I do the experiment. Yeah.
21 possible outcomes.
There are, well, it depends on how we call. So if you think about it, like there's only 6 outcomes in the sample space, but this outcome happens 6 times as likely as this outcome. Yeah. Yeah. Mm-hmm.
There's like 21 dots in the die.
Well, I mean, I guess you could view it that way, but sort of mathematically, why do I need the denominator of the probability to be 21?
The summation of R sub x.
The summation of all these probabilities has to be what?
No, like up top, the R sub x, so you add.
Oh, that's true, that if I add all these up together, but and that happens to be the case here. If I were to define the numerators a little differently, though, it might claim the denominators would be different. Yeah. The sum of the probability has to equal what? That's what I'm looking for here. Is that, so I can give you an outline like this where I say, I don't tell you the probabilities, but I tell you the relative probabilities. I can say that the outcome of 6 showing is 6 times as likely as 1 showing. 2 is twice as likely, 3 is 3 times as likely, and so on. I haven't given you the probabilities, but you know that if those are all of the outcomes, all the probabilities have to add up to 1. So I can fix the numerators because I kind of know that this is going to be 6 times that, this will be 2 times that, 3 times that, and so on, but I don't know the denominators. But if I add up all of these things and solve for the denominator, then I find out that it has to be 21 for all these to add up to 1. Yeah.
So basically you're kind of like adjusting like your function for it to fit 1.
That's right, exactly. Yeah, so it's, again, going back to this table example, I could give you the weight of a slice of this table in grams or in pounds, but I might be more interested in fraction of tables. And so I could say that, you know, this slice weighs 1/3 of the table. So now table becomes my unit. So my sample space of all of the possible things that could happen out of the die, that becomes like my maximum weight. And so I know that all of the outcomes have to add up to that weight, and I'm just arbitrarily calling that weight 1. And so that's why, even though the numerators are clear from this statement up here, the denominators I can solve for to make sure they all add up to 1. All right, questions of that? So we can verify all the probabilities are greater than or equal to 0 for all 6 outcomes. And we can verify that the sum across all of the outcomes, across the whole range, is equal to 1. The sum of the probabilities. I guess I should have a little p x of I right here. I think I just shorthanded it when I typed this up. All right, and the way we represent that graphically, the so-called discrete probability distribution, is with these things called Dirac delta measures. It's sort of the formal name of that. And they look like pins here, and the basic idea is that they are loading up mass on each particular point. We're saying that at this one single point, there is, whatever I said, 1/21 of the mass. At this point, there is 6/21 of the mass. But they're only at that particular point because it's a discrete distribution. So instead of having mass spread out over a continuous space, it's lumped. And those lumps are concentrated here. And in measure theory, we would use something called a delta measure in order to concentrate mass into one place. And that's what is depicted here. So when you see PMFs, probability mass functions, so the discrete probability distribution, that's this table. And this graph up here is the probability mass function. And so that's just, you know, that's what these little spikes are for. It's not defined outside here. It's 0 everywhere else. It only gets a probability at these particular points. So depicting that mass function. Questions about any of that? Before we go on to continuous, where continuous probability distributions tend to be ones where coming out of 380 and 385, we see the most kind of confusion as to what the heck this density is. All right. So continuous random variables are ones where the range are intervals or sets of intervals. So they aren't defined at one particular point, they're defined across a whole space. So a probability now is usually given in terms of an interval. What is the probability of an interval? I'm not asking for probability of one number. I'm asking for an event. I'm asking for the probability that an outcome was between A and B. And in order for me to define that, I have to use this funny thing called a probability density function, which is not a probability. We'll get to that in a second. But in order to know the probability of anything between A and B, I have to take the integral under a curve between A and B of this density function. So I plot this density function, and the area underneath here is the probability that I'll get an outcome that'll map to a value between A and B. But the individual value at A is not the probability of A. We'll get to that here in a second. But the basic idea here is that these density functions, like probabilities, they have to be greater than or equal to 0. Similar to probabilities, they have the integral under them has to add up to 1. But the big difference is that they do not have to abide by the rules of probability otherwise. A density can be greater than 1 because it's a density. So it's like a glass of water. A glass of water weighs a particular amount. It might weigh, so there's 8 pounds per gallon of water. So 1 gallon of water weighs 8 pounds. But the density of water throughout that gallon is some other number, and it has some other units. It should not be surprising to me that the density of water expressed in some other unit might be greater than 8. If it was 8 pounds per gallon, I have a gallon of water. Density is in a totally different unit than probability. And so you can have densities that go all the way to, they're unbounded. But it's kind of like this table. This table has a uniform density. It's the same density across it all here. But you can imagine you could build a table that's heavier on one end and lighter on the other because it has maybe more dense materials on one side than another. And if I took a slice through the very dense area, if that slice was infinitesimally small, it would weigh nothing. But the density of that slice might still be extremely high, and the table would still tilt towards that dense side. So that's why we call it a density, is it represents, if you were to integrate under it, you would get probability. But it is the probability density. It's like the probability per square inch. If you're thinking of this here as an inch on a table, and this here is the density of the table, then the density is sort of telling you that how much weight do you add by going another square or another inch over? How much weight do I add by integrating under another inch of this density? So that's why we use the term density, and that's why it is not the same as probability. And if I show you a probability density function that goes well above 1, that's perfectly okay. So the other weird thing about it, which I've already sort of talked about, is that if even though a density function might exist at a point, the probability of any particular point is always 0, because probability is weight. If I take an infinitesimal slice of the sun, it weighs nothing, even though the sun is super, super dense. So any questions about that? The conceptualization I'm trying to get you to think about is when I show you a probability density function and I ask you for the integral from x0 to x0, or the integral underneath that, what you should think about in your head is not a probability density function, but a chunk of mass shaped like that is sort of going to be heavier over here because there's more mass there, and lighter over here. And what I'm effectively asking you for is how much weight is in this chunk, or how much weight is in this slice. A slice is always going to have no weight, but a chunk, it's going to depend upon how much mass is in that chunk. And so that requires me to sort of add up the high density here and the low density here to figure out how much total mass is in the chunk. So it's all about how much is in these chunks. And so it really helps you with probability if you can conceptualize it as chunks of mass that you're breaking up into parts. Questions about that, about continuous probability distributions and their relationship to mass? Yeah?
So you mean the slices in like having x equal to something?
Right. The probability of x equal to x0 is always 0, regardless of what the density is. Other questions? All right. So an example that we might model with a continuous distribution might be the lifetime of a device that inspects cracks on an aircraft wing. We have no idea when that thing is going to fail. It could fail at any instant of time. And so we are then going to assign a density of probability to every instant of time. And then you can then ask, what's the probability that it will fail in any interval? And so that's kind of what we've done here, is that at every time, so x is time, so this is like when it was, maybe this is when it was first built, and this is how long it's been in use. And so at any particular time, we only can associate a density of like, what's sort of the likelihood, what is the extra probability that would be added if we already had calculated how much, what's the likelihood that it would fail up until a particular point, and we added a little bit more to that. And so that's what this density is representing. But the actual probability is the area underneath that curve. And this is what's the probability that it will fail between years 3 and 4. You know, or what's the probability that it will fail after year 3, and you'd have to fill this whole thing out. And so if we think of the other way, what's the probability before year 3, then again you get that interpretation I was just talking about, where the density sort of represents what's the marginal addition to that probability you would get if you moved the 3 out a little bit. And that sort of represents this idea of density. So the density itself is not the probability. The area underneath the density is the probability. And that allows the density to sort of be unbounded. So if I give you these questions where I ask you, is this a probability density function, you should not be looking for something that is just under 1. All right, so I mentioned up here that we might model this as an exponential random variable with mean of 2 years. And I haven't defined what we mean by mean, but we will in just a moment. And if you are sort of probabilistically minded, then you'll see that that's a pun. And if you're not, you'll get it in just a moment. All right, so the other sort of quick things we need to define is the cumulative distribution function. So this is defined the same way for both discrete and continuous. This will be really important. You're going to have to solve for these on homework D2. It turns out these are often more useful than the probability mass functions and probability density functions. They're defined just as the probability that your random variable is less than whatever the argument of the function is. So f of little x is just the probability that the random variable is less than little x, less or equal to little x. So for a discrete one, you just add up all of the outcomes less than the argument. For the continuous one, you integrate from minus infinity to x. And something that will be really important on your homework, for homework D2, is that you have to remember you can split those integrals up. So if you end up finding yourself integrating from minus infinity to x, and you know that x is greater than 0, then you could just integrate from minus infinity to 0, and then also integrate from 0 to x. And this thing right here becomes a constant with respect to x. And this thing ends up being the function of x. And so this will end up being a trick that you'll have to follow over and over and over again in homework D2. And if you don't, then you often forget about the contributions that have been added to earlier cases. And this will become more clear as we move on. But if you're already looking at homework D2, then I just want you to have this in your back of the mind. You're going to have to split these integrals up over and over and over again in order to make those calculations go. All right, so the properties of a CDF, which you should remember when you're doing homework D2, when you're asked for a CDF to validate that you've done things right, is it's non-decreasing. If your CDF drops at any point, so it was equal to 0.5 at value when x is equal to 2, and then at x is equal to 3, it's now down to 0.25, then you've probably maybe left out one of these things. So it should always be non-decreasing. It should never jump down. It should always be climbing. The rightmost value should be equal to 1. the leftmost value should be equal to 0. That's always the case for every single CDF. So if you solve for a CDF and it's not 1 at the very rightmost value, then you've done something wrong. You need to go back, and again, you might have left out one of these things. If you've solved for the CDF and it's not 0 on the left, then that also indicates there might be something wrong. And then a useful property of a CDF is if I ask you on a midterm, for example, I might give you a probability density function, and I might just give you the CDF. And then I'll ask you to calculate the probability that the random variables in between A and B. Now you could go through the calculus of integrating under the PDF, but if you already have the CDF, all you do is you evaluate the CDF at the upper interval, and then you subtract off the CDF evaluated at the lower interval. So it's already done the integration for you. So it's a really useful trick with CDFs. So as an example, so this here, we have our outcomes from before. These are our 6 die where the probability is proportional to the number of dots on the die. And so this is our probability mass function here. And the cumulative distribution function is just, it always is equivalent to the mass function in the first value after the 0. So that's 0 out here, and then it jumps to 1 over 21. But then after that, it just keeps accumulating. So 1 plus 2 gives me 3, plus 3 gives me 6, plus 4 gives me 10, and so on. And if I plot the CDF, I get this stair-step looking thing, which is 0 on the left and 1 on the right. Now, an interesting thing about this CDF is if I draw a random number between 0 and 1, and I plot that random number, and then see where it hits the CDF, and then bring out the outcome there, if I do that over and over and over again, these outcomes will actually be drawn according to these probabilities. So this I talked about a little bit in lab 3, but this is a way in which you can actually draw outcomes. You go into Excel and you can draw these with equals rand. And if you then have the CDF, you can then draw outcomes according to that PDF. So that's one of the ways CDFs are useful. Similarly, here's the CDF for an exponential. The exponential, remember, it has a ski slope sort of shape like that. If I integrate under that, it ends up having this decaying shape like this, 1 minus e to the minus x with a constant out. And similarly, if I were to draw a random number and put it on this axis and then see what it maps to on this axis, I can take something that's drawn uniformly between 0 and 1 and translate it to something that is drawn according to this exponential. So whenever you go into Arena and say, give me an exponential with this average, behind the scenes, it's doing this. It's drawing a random number between 0 and 1, and it's stretching it out in this way to give you a random number that's exponentially distributed. And that'll be what we learn how to do in lecture E2. Questions about, yeah?
Just, I'm going back to the other graph real quick, just wanted to clarify, like, it's in like the exponential, like, goes like this?
The PDF of the exponential goes like that.
Oh, you're graphing the PDF.
And this is the CDF.
Oh, okay.
So this is the cumulative distribution. All CDFs, discrete or continuous, start at 0 and limited, or at least limited by 1.
Oh.
They start at 0 and end at 1. Yeah.
So since that is the graph for the CDF, if you actually wanted to know the probability of a value happening, then you could just take like a value of x and then find its value on the y-axis, right? Since it's the CDF.
Good question. So if I knew that, so I don't know if I can, not in this, but if I knew that I could, if I wanted the probability that x is equal to 4, like say it was right here, this doesn't tell me the probability that x is equal to 4. This tells me the probability that x is 4 or less. So a CDF tells you the probability of the event that the random variable will be less than whatever that you're asking for. So this is saying, like, if you ask for the CDF of an exponential at -2, we know that there are no outcomes below 0 in an exponential, so that probability is equal to 0. If I ask for, all right, so if the exponential gives me an outcome, or if the PDF tails off, so there's almost no density out here, if I ask for, all right, well then what about 10? Well, I'd say almost all of the outcomes are less than 10, so that's why the CDF is near 1 there. So the particular value of the CDF is not the probability of the outcome, it's the probability of that outcome or less. Any other questions? All right, so then the last definition we have here is for this mean. And then I want to take a couple of slides to go over the lab results from lab 3. The expected value, otherwise known as the mean or the first moment, so that's where the moment joke came from, that this is defined this way for discrete random variables. It's just the sum of the probability multiplied by the outcome. For continuous random variables, it's the integral underneath the function, which is the outcome times the density. And so you say, well, what is that? You know, why do we care about this quantity? Well, if you think about it physically, here's a PDF of an exponential. Here's its mean. So if you just happen to calculate it, it's right there. That is where you balance if you were to turn this into a block. So this is, if you were to put a little fulcrum right at the mean, I could take an exponential, and if I wasn't getting on a plane after this class, I would have brought a piece of cardboard in that I'd cut out according to different distributions and kind of showed that I could balance them on my finger where the means of those distributions are. So you can try that exercise at home. But if you cut out an exponential and draw its mean, that's where it balances. If you cut out a beta distribution and draw its mean, that's where it balances. And so physically, the mean is the same thing as the center of mass in a physical object, and it is literally the center of mass in a probabilistic object. So if I show you a probability distribution, you should be able to guess where the mean is just by using your kind of physical intuition that, like, if I had an object like that, the mean would probably be around here. And then, you know, talk about outliers and things. If we made this skew even kind of longer, then what it's going to do, it's going to put more mass out here, and that's going to then shift the mean over. In other words, in order to keep this thing balanced, I have to move this little fulcrum over in order to keep it in balance. And that's why if you add a bunch of outliers, it's very sensitive to the mean. It's moving that balance point over. So that's the physical interpretation of a mean, the meaning of a mean. The other moments that we care about are the so-called higher moments, which look just like the mean, but we then raise the outcome to a power. So the second moment, that's the expectation of x squared, is just x squared times the probability, either in the density case down here or the probability case down here for discrete and continuous. We care about those because they help us define things like variance. The variance is the so-called second central moment. It's a central moment because it's the outcome or the random variable minus its mean. That makes it central. And then it's a moment because you're taking the expectation of a function and you're raising it squared, so that makes it the second central moment. So the second central moment is just the variance, and the variance is a measure of the spread of the distribution, so we'll see lots of examples of that as we move on. And there's this convenient thing that if I give you the second moment and I give you the mean, I can then calculate the variance. And so I don't actually need to go through this math, because if I just do the second moment, I can then calculate that. So if you look for any distribution, they often give you a table of moments. They mainly don't give you central moments. And that's because it's easy to calculate central moments with formulas like this. You don't have to actually go through this math. So the standard deviation is just the square root of the variance. We just like to put variance in the same units as the random variable, and so we take its square root, but otherwise it's a similar sort of thing. And we're often going to use sigma for standard deviation and sigma squared for variance. So those are the notations you're going to see throughout the class. Yeah?
What are some examples of non-central moments?
So this is this is a non-central moment. So it is a moment. What makes it a moment is it's the expectation of a variable, or it's expectation of a function. And so it's a moment because you're going to take underneath the integral, you're going to integrate this thing times the mass. We call it in mechanics, we call it a moment because you're taking mass as distance. And so the probability is the mass, and the distance is kind of like this thing into here. So the expectation of anything other than x is a moment. And then the central moment is just subtracting off the mean. So a non-central moment is just when you don't subtract off the mean. That's all I'm sort of saying. So this is the second moment, that's the second central moment. Any other questions? All right, well, let's jump into some lab stuff. So in D2, before I get to lab stuff, we're going to look at the common distributions that you'll use as input models in this class, so you can gain some insight as to when to use uniform and when to use normal. We'll use for both continuous and discrete, and we'll then introduce a little bit of queuing theory, not much, because most of that's in 470, but we kind of link all that together. All right, now, lab 3 that you guys did. So you did this Monte Carlo analysis, which hopefully will make a little more sense in light of some of the stuff we've talked about here. And so the big essence of Monte Carlo sampling is I am going to generate a computer function which generates outcomes that are consistent with a desired probability distribution. And then I will then do experiments on that probability distribution in order to get something useful out. So I might take the average of those samples, and maybe that average ends up telling me a useful computation. And so an example of that is when you look at this randomly distributed dots around a rectangle. If you then put a circle inside it, you say what fraction of the dots land inside the circle as opposed to outside the circle. And you just say, well, that's easy. That's the area of the circle divided by the area of the square. And that comes out to be pi over 4. And that's interesting to us because that means if we do this experiment, the fraction that we estimate inside the circle will be an estimate of pi. So we can simplify this a little bit by zooming in on the corner, and still the ratios work out the same way. And then we run this experiment in Excel where we generate a random x coordinate and a random y coordinate. That's this column and this column. And then we do a little formula like this one. If you can't read, it just said if the x coordinate squared plus the y coordinate squared is less than or equal to 1, well, that defines the inside of a circle. Then I'm going to replace it with a 1, otherwise replace it with a 0. And if I took the average of that column, that average will be pi over 4, or be an estimate of pi over 4. So I just multiply that average by 4, and I get an estimate of pi. And that estimate will get more and more accurate as we get more and more rows. Now, a lot of people, and I'm glad you brought these things up, and I've added some clarifying remarks so it isn't so scary to the next sort of groups, but since I had you this semester add a doc file, you notice you're like, oh shoot, every time I save my Excel spreadsheet, I get different numbers, and so when you look at my doc, it's going to look different than my Excel, and I don't want you to think I cheated. So I got tons of those emails. And that's totally fine. It helps reinforce this point we made here, is that every time you save in Excel, it reruns the experiment, and you get a different outcome. So you get a different estimate of pi every time. And so if I took all the distributions, like this right here represents for 500 samples, this is the average coming out of an experiment like that, and this is the standard deviation. And I end up getting, actually this is the standard error of the mean. So basically the SEM, the standard error of the mean, we can take a distribution of all the means that each one of you calculate every time you resave in Excel. It keeps coming to a different number. And with only 500, that estimate of the mean itself is going to land on a distribution with this large standard deviation. So that's why every time you save, sometimes you got values really close to pi, sometimes very far away from pi. But if you did 1,000 lines, then you would have much more consistent numbers every time you save in Excel. And if you went all the way up to 1,000,000, then it would pretty much always look like pi. Now, what we'll get into after the midterm is ways in which we can basically turn the standard error of the mean into a confidence interval. And a confidence interval is a visualization of a t-test. Everything inside this 95% confidence interval could not be rejected by a t-test. Everything outside the confidence interval would be rejected by a t-test. And so what you see here is as I increase the number of samples in Excel, what I see is there's pi, 3.14159, etc., always goes through the confidence interval, regardless of how small the confidence interval gets. And that sort of gives us confidence that this is approximating pi, is that we never can reject pi as a possibility. We can reject 2.85 all the time. We can't reject 2.95 until we take more data. And now we can reject 2.95. And as we take more and more data, we never can reject pi. That doesn't mean that pi is the population mean, but it does mean that it always fits into a neighborhood that has possible population means in it, and that neighborhood gets very, very tiny once we're done going into samples. So that's what you sort of saw there as you estimated pi. But the big takeaway I wanted to take away for this part of the semester is just how to generate these 0, 1 random variables. You'll need this in homework D2 because you're going to have to generate some of these histograms yourself. Then in part 2, we had these multi-part activities where you had one activity in parallel with another and another, but the first activity had 3 subparts, the second activity had 2 subparts, and the third was its own activity, but they all had the same average. And you can implement that in Excel, and I kind of, this is the idealized one, where you can basically add 3 random numbers together in one column, add 2 random numbers together in one column, and then just have a single random number in the other column, take their max across all the columns, and then find the index of which column was equal to that max. And that allows you to get a distribution of critical times as well as a distribution of which path was the critical path. And when you do that, the sort of surprising thing is, in the distribution of critical times and the means of these, is that the mean is higher than 9, even though the mean of each individual path is equal to 9. And we kind of talked about a rough kind of hand-wavy reason for that, but basically, because we're taking the max, you have to get really, really lucky to ever be less than the max, because it's more common that one of your 3 paths is going to be over the mean. So, even though the mean is 9, in order for the max to be less than 9, all 3 have to be less than 9. And it's going to be much more common that at least one of the 3 is more than 9, and that's what shifts this thing over so that your average is more like 10.1. And then, but then also when you look down at the critical path distribution, it might have been a little surprising to see that the path that had 3 subactivities was not very often the critical path. But the path that just had 1 activity was very often the critical path. And if we were to actually take a histogram of each path separately, then we'd see that the bottom one was very likely, it had sort of density throughout, uniform density across all possible outcomes. But in the top one, because each subpart would have to be at its maximum in order for the sum to be at their maximum, that was extremely unlikely. And so the reason why you see this bias towards the bottom one being the critical path is that it actually has probability that is still highly represented over here in the high times. Whereas as you keep adding these together, the central limit theorem kind of pushes their tails down, and so they become much more clustered just around their mean. So that was kind of the interpretation. But the big takeaway message I want you to take away from that is how to generate these uniform random variables by scaling these things. And so we talked about, there's this formula, so you can take rand, you multiply it by how big the range you want it to be, and then you add the lowest number of the range, and that realizes a uniformly distributed random variable between A and B. So the message here is that we can take one type of randomness and turn it into another. So let's unpack that a little bit. So this is the thing that I talked about in the lab and a little bit earlier today. If I have 3 outcomes with desired probabilities, I can then say, well, you know what? A uniformly distributed random number between 0 and 1 has a really nice property that it's very easy for me to get outcomes with set probabilities. If I want an outcome to happen 20% of the time, well, I can just say, well, how often is a uniformly distributed random number less than 0.2? Well, 20%. How often is a uniformly distributed random number less than 0.7? 70%. If I then subtract those two and say, how often is a uniformly distributed random number between 0.2 and 0.7? 50%. So this shows me that if I want to generate outcomes according to these probabilities, all I need is a way to translate from these probabilities into these kind of cut points on the uniformly distributed random number. And I can then set up a nice mapping where I say if my random number in Excel comes out to be between 0 and 0.2, give me a 1. If it's between 0.2 and 0.7, give me a 2. If it's higher than 0.7, give me a 3. And these outcomes will be drawn according to this probability. And I already mentioned earlier in the class, if you just form the cumulative probability, then this happens for free, because these become your your cut points. So now the first one, 0.2, that is the upper bound for outcome 1. 0.7, that is the upper bound for outcome 2. And 1.0, that's the upper bound for outcome 3. So I can now write a little Excel program, and I did this in one of the videos to do this, but if I want to sort of show that graphically, I show the CDF, which we introduced today. I invert the CDF, which you're going to do on homework D2. So I'm basically going to flip outcomes on the y-axis and the CDF on the x-axis. So I'm just flipping it across the diagonal. So you can do that mathematically by setting up this equation and then solving for O. So that flips the two. And then at that point, I now have a mapping from 0 to 1 onto my outcome space. So if I go into Excel and I generate random numbers between 0 and 1, then I go up here and that tells me which outcome corresponds to 0 and 1. And so that is a generic way of generating whatever outcomes you want according to whatever probability distribution you want. And I can do it in the continuous case as well. So to bring you guys back in, for those who've fallen asleep, what is, if you look at this cumulative distribution function, can you tell me what distribution that represents? What is this an exponential? Is this a normal? What is this? Take 30 seconds and talk to your neighbor and tell me, what does this cumulative distribution function represent? What distribution is that? Chat. All right, so from this side of the room, I'll ask a sub part of that. So everybody in this side of the room, tell me, what is the lowest outcome that you could get out of this distribution? 2, okay. So on that side of the room, what is the highest outcome I could get out of that, out of this distribution? 4. So I can't get anything lower than 2. I can't get anything higher than 4. So now I have to use this slope. So what then, so does any guesses then as to what distribution does this represent? You can already take a pretty good guess, like, we already know of distributions we've used in this lab that are never less than 2 and never greater than 4. So the real question is, what does this shape represent? So what distribution might I be fishing for? Yeah. Uniform, right. So the fact that this is a flat slope, if I took the derivative of the CDF, it would be flat. So a uniform density. The density of this CDF is flat. If I had a table that as I went from left to right, it got heavier and heavier as a line, that would tell me that the density of the table was uniform. And so this is a uniformly distributed random variable between 2 and 4. So if I invert it, because I'd like to generate a uniformly distributed random variable in the same way I just did with the discrete case, again, I'm just going to set R equal to this and then solve for O, which is what I did over here. That rotates it around the diagonal, and now I have a mapping. So between 0 and 1, if I generate a number between 0 and 1 and find out where it lands, it's going to land between 2 and 4. And the function here is exactly the function that you guys have been using. So this inverse transform method that we'll learn in lecture E2, a special case of it is the formula that you guys were using in lab 3, where you're multiplying by the range and adding the lower end of the range. And so the idea here is that I'm trying to get to take away from this is if we have uniform randomness between 0 and 1, through a little bit of math, we can turn it into whatever distribution we want. And that's what ARENA's doing behind the scenes, that's what Excel's doing behind the scenes, and when you start going to Lab 5 and implementing expressions, if there's a distribution that is not in the catalog, you can do this behind the scenes yourself. All right, so this is what you'll practice on homework D2. I might give you a PDF, and you'll have to solve for the CDF, and once you have the CDF, you can then solve for the inverse CDF, and then use that in Excel to draw samples from that distribution. So that's basically homework 2 in a nutshell. So I'm going to put up the attendance question, and then I'll ask for questions while it's up. So my question here is, when you take the derivative of a cumulative distribution function for a continuous variable, what do you get? Continuous random variable, what's the derivative of the cumulative distribution function? And with that, I'm happy to take any questions, and that's all I have for you today. And again, no class on Thursday.
Is it his first kid?
Yes.
Oh, you did? Looks really great. Oh, it looks. Did you go to chat?
Yes.
It looks really great. Wait, are you like going today?
Yes, I'm going right now.
Okay, but my line. Okay, go change, and then go like this, and then go.
Yeah.
Look, okay, just give me a second. Okay, so number 1, the and then number 2, what version of deadlines? So I noticed that there's a paper bonus due on Monday, and then homework 2 is for Tuesday as well as an interactive canvas activity. So my question was,